points. Don't worry, we will be more or less on time. Correlation, back to correlation again. This is what I told you about already on the day one, right? That if I have and use the same example, that we could compute the correlation, a number between -1 and 1, that summarizes the value. And let's try to, while we get to the correlation, because there is also a correlation. Actually, maybe not. There is something called R squared, which is actually exactly the square of the correlation coefficient as you were told how to compute on day one. It's the square of this number that I told you, which is given by the procedure. For these data, the square apparently is 0.92, and we have some interpretations of that. But let's just, while looking at that, also just dwell a little bit on the different outputs. What are we told by this summary output? I brought a slide that tells us, I'm summarizing the different information given to us by this summary function in R, right? It tells us a little summary of the residuals. The residuals are the individual deviations. Let's do the summary and look at it maybe just to make it explicit. Here we are. That's what I'm talking about. What are we told by R here compared to what have we learned, right? It gives us a summary of the residuals. It's basically just giving the quartiles and the mean and the minimum and the max. So it tells me, for instance, that among all the persons in my data set, the guy who deviates the most below the line, he is almost 6 kilos below what the line is telling that he should be. And on the other opposite, the guy deviating the most above the line, he is about 6.5 kilos above what the line otherwise would predict him to be, right? And then on average, we have the median and the first, we don't use that. But it's a summary of those individual deviations, the residuals. And the last part, the 8th part, is dealing with looking even more at residuals, just so we get back to the residuals in a sec. Then we have discussed this a lot. Let's see, I think I summarize it in my slides. We get the estimates. That's the way it's the heading of this object in R is called coefficients, and then the coefficients is the name for a beta 0 and beta 1. That's the coefficients of the model. We get how they are estimated. We get the standard error, as I've told you, right? We've seen the formula also, so we could compute it ourselves if we want, but R is giving it to us. We get a t-statistic, which is an observed t-statistic for this hypothesis, as I told you, for the 0 hypothesis. Very often, the relevant hypothesis for the slope, at least, that is the basic thing telling us, is there at all a relation between x and y? We check the p-value. If it's low, yes, then there is a relation. If the p-value is not low, there doesn't seem to be a relation between x and y. This is very often ignore the t-test for the intercept, right? R is by default testing the intercept equal to 0 and giving you the result of that hypothesis test. Think of our height-weight data. Does it make sense in that set to test whether the intercept is 0? Well, at least it's not. Our intercept was minus 120 kilograms, right? So definitely not 0. But what does that tell me? Rien, nothing. Nada. Nix. We get some stars also, 1, 2, 3 stars. That's a classical, not only in R and this procedure. 1 star, that goes with our table of interpreting evidence of the p-value. 1 star means below 5%, 2 stars means below 1%, 3 stars means below 1 per mil. It's a global kind of code that I use for those 3 levels of evidence against the null that we also explain in a table in chapter 3 to you. Then we get, with a slightly confusing name, but nonetheless, we get under the name in the R output, residual standard error, right? Residual standard error. We get the value of sigma hat. We get the estimated value of sigma hat, simply. And we also get what is the degrees of freedoms. The n-2 value is told us if we would like to use it ourselves for finding t percentiles, we get the degrees of freedom told to us. And then we get this multiple. It's called, and today, next time we'll know why this name pops up, but it's called multiple R squared, and it is in fact just the square of the correlation coefficient for these type of data. It is just the square of the correlation coefficient. And here it comes then. We give such the Rasten we do not use in this course. Fantastic. We have a nice interpretation related here, where we sort of link the 2 ways of looking at data, the correlation way and the regression way. Because it turns out, it needs a bit of thinking actually, but now you can trust me, or you can dig into the formulas. When you square a correlation is between -1 and 1, right? Then if you square it, it's between 0 and 1. And if you interpret that between 0 and 1 as a percentage, which we do sometimes, we can interpret it as the amount of y variability explained by x. So when the correlation is 0, no differences in y is explained by x. When the correlation is 1, everything which is going on in y is explained by x. Right? The formula that could help us understand it a little bit, but is the fact that it turns out that the correlation coefficient that I defined to you in chapter 1 can also be expressed like this, where the raw variability, this is the variability where y is compared with its own mean, and this is the variability where y is compared with the line. The y hat is the line value. It turns out that if the line does no better than the mean of y itself, which means that we have no use of x at all, this one becomes 0. If the line predicts the y exactly with 0 error, of course never happens in real life, but scenario-wise, let's imagine that it would, then it gives 1. I mean, yeah. So R squared is also called sometimes coefficient of determination, or forklaringsgraden, the explained variation, percentage of explained variation of the y. X explains, the height explains some of the weight differences we see, but not all. How much does it explain? Well, 92%. The squared correlation was 90.92, right? So 92% of the differences in our heights, differences in our weights, can be explained by our differences in heights. It's pretty high on these data. The remaining cannot. The remaining is remaining biological differences in other ways. Okay. There is a link. We're not going to dwell on this a lot. There is a link between the correlation and the slope. The correlation is a measure of linear relation, as I told you. When the correlation is negative, the slope is negative, or when the slope is positive, the correlation is positive. I mean, they have the same sign because, in a way, the slope tells us, using the units of x and y, how y relates to x. The correlation is a unitless measure of the same thing. And statistically, we could, in many contexts, not always, but many times, we could talk about statistics, hypothesis testing, for the correlation. But in a way, it's nothing new. We've already done that. It brings nothing new here. It's the same. I mean, having a hypothesis of zero correlation is the same as hypothesizing zero slope. So we can just as well do it on the slope. We don't have to do it on the correlation. It's actually theoretically more complicated to do on the, although you can not the hypothesis, but that's the same. But confidence intervals actually on the correlation, you can do that also. But that's more challenging, actually, at least theoretically. So that leads us to the final part, and I go 3 minutes over. That's how much time I'm going to use on the last part. We'll get back to that next time and do more on this part. Because. We need to think about whether our linear model is the right model. Right? We assume a line, so if we're going to use it for real-life applications to predict something in some tablets at Lundbeck or height of a weight of a young guy here, we should, of course, hope or believe, or it's based on the assumption that the linearity is the right model. We have to be critical about that, self-critical. The way to check that, we talk about that we check the assumptions of the model, or we do model control in statistics, or model validation, or model diagnostics. There are many words for the same thing. We should think about whether our residuals are normally distributed, whether they have the same variability, no matter where I am on the line. That was one of the assumptions. I talked about that. Non-trivial assumption.